Okay, we have a bit of time, and let's start talking about the next topic, which is the errors in solution of differential equations and how to improve or reduce these errors. So first topic is something that people may have heard about if they dealt with numerical solutions of various kind of differential equations. What is numerical dissipation and numerical dispersion? These are different types of errors that affect numerical solutions and of different origin. So the way to analyze them is what's called the method of modified equations. Dispersion and dissipation, they are both concepts in differential equations. Dissipation means high frequency components get smoothed out, right? So it's like we are solving the heat equation. By adding a second order derivative term to the equation, we see that very high frequency oscillations get smoothed out very quickly, and the lower frequency oscillations they damp at a much slower rate. So that's what dissipation is. And dispersion is different. It's also acting at different frequencies in a different way, but they are not reducing the magnitude. Instead, dispersion means they move different frequencies at different places. So higher frequency goes that way, lower frequency go that way. That's dispersion. Okay. And what's numerical dispersion and dissipation? That's the kind of dissipation and dispersion that is not supposed to be in the behavior of the original differential equation, but is introduced by using numerical approximations. So a primary way of analyzing numerical dispersion and dissipation is in looking at this very simple linear advection equation. du dt plus du dx equal to 0. So everybody by now should know what's the correct behavior of this differential equation, right? Right?
Well, there should be a u in there.
Yeah, let's say u is equal to 1, okay. Right? So basically, it's a differential equation that is supposed to advect anything, low or high frequency components at a fixed speed of unity towards the right hand side, right? Okay, or we know that u of x and t should be equal to any function of x minus t, right? If you plug this into this equation, you'll see the right hand side equal to 0. It's exactly satisfied. So the correct behavior of this differential equation is that it moves all components towards a single direction without damping, right, at the same speed. Now let's see, if we use numerical methods to solve it, would it be the same? Okay, so let's say if we just discretize space without discretizing time, so then we get an ordinary differential equation, right? So let's first say, what if we use upwinding, a first order upwinded differentiation? So what would a first order upwind scheme be like in discretizing du dx?
The I plus 1 minus ui over delta x.
Sure, so the wave moves towards the right, right? Which direction is upwind direction? Which direction is the wave coming from? It's from the left, right? So an upwind would be
I minus I.
Yeah, it would be involving I minus 1 instead of I plus 1. So it would be ui minus 1 divided by delta x equal to 0. Anybody have a question? No? Okay. So let's see, what's the behavior of this equation? Okay, we all know that this is only a first order approximation to the differential equation, right? And first order may not be very good. And the method of modified equation, or the analysis using modified equation, is the idea that although this numerical scheme is only a first order approximation to that particular differential equation, maybe it is actually a higher order approximation of a slightly different differential equation. And how do we find this out? We do Taylor series analysis again. Okay, let's do this. Let's do the Taylor series analysis as if we are trying to find out the order of accuracy. And we'll see that we automatically obtain a different differential equation for which this is a better approximation. Okay, so let's say the only thing we want to do is this, right? So it's equal to ui minus delta x times du dx, and plus delta x squared over 2 d squared u dx squared. So let's stop over here. This is enough for this particular scheme. When we plug it in, we get dui dt plus, okay, ui minus this is cancelled out. So what we get is plus delta x times du dx minus delta x squared over 2 times d squared u dx squared over dx, right? Equal to 0. Well, this is all at grid point I, right? And since this applies to everywhere, so let's now just start to write partial derivatives. Du dt plus the delta x cancels out. We have du dx. But now we have another term. Let's move this other term to the right-hand side. This other term is delta x over 2 times second order derivative of u. And we should all know like what a second order derivative on the right hand side with a positive coefficient do to this advection equation. It becomes an advection diffusion equation, right? And the amount of diffusion you have is half of delta x. So yes, as delta x goes to 0, the diffusion actually goes to 0. But with any finite delta x, we have diffusion in this equation. This is why this is the modified equation, right? This is the modified equation. And the first order upwind is, yes, actually a first order approximation to the original differential equation, but it is actually a second order, at least a second order approximation to the advection diffusion equation. And the additional diffusion term explains the behavior of the first order upwinding scheme, which actually diffuses out the solution, right? It damps down the high frequency oscillations. And if you remember, we tried this scheme and we had a square wave as an initial condition and the periodic boundary condition, and the square wave goes around the domain for once. Instead of a square wave, we get a much smoothed out wave. Right, we get something more like a Gaussian. So this is basically the idea of the method of modified equations, to analyze the behavior of numerical schemes to figure out what kind of error do we introduce and how does it manifest in the numerical solution of the differential equations. So we'll come again next lecture. Oh, by the way, I may have to cancel the Wednesday's lecture. I will announce today when we are going to make a makeup lecture. So if you have plans for go early for Thanksgiving, you're free to go. All right, so I'll see you next time and continue the method of modified equation into the behavior of other numerical schemes and how do we improve our numerical schemes based on the analysis.